Okay, gang, here goes. It's 10:15 on Sunday. I'm sorry I can't make it at school for Monday, but you know, sometimes we don't feel well, sometimes other people don't feel well, and sometimes we gotta do what we gotta do. Um, right, so continuing on to 16.2, which is concentration of solutions. Um, Concentration has a particular definition, and it is the amount of solute in a given amount of solvent or solution. And we're going to use four types of concentrations. You are expected to know all four of these concentrations according to the standards. Okay, so we're going to, so we continue. And so you'll notice from the bottom that they're going to know, uh, I think it's standard 6D, that you guys need to know all four of these kinds of concentrations. So we're going to start with the easy one, it's the simplest one that's out there, and it's the grams of solute per liter of solution. This is sometimes used for aqueous solutions where the solute is a solid. So, for example, we're going to dissolve salt in water. The example is, if we use 35.0 grams of sodium chloride dissolved in 425 milliliters of solution, okay, how many grams per liter is that? Well, the key is to convert your milliliters to liters by dividing by 1,000. And so we'll start with 35.0 grams. Okay, and we know the solute, it's going to be solute divided by solution. So we're going to take our number of grams and divide it by the amount of solution we have. That's grams per milliliter. But we're really trying to find grams per liter. So we know that there's 1,000 milliliters in 1 gram, I'm sorry, 1,000 milliliters in 1 liter of solution. And so the milliliters will cancel, we're left with grams per liter, and we just multiply across and divide, and we wind up with 82.4 liters, or grams per liter. And that's the concentration, and that's it. Unfortunately, that is the easy one. That's as easy as it gets. Now, we'll have more practice with this with some other problems in your packet. The next one kind of steps up from there because, for the last couple months, whenever we see grams it's nice for us to deal with because we're used to dealing with a mass of some kind, but we don't do chemistry in grams. We do chemistry in moles. And so we have one specifically for moles, and concentration using moles. Now is the number of moles of solute per liter solution. Now you can kind of see where we're going to go from here. Okay, so molarity, is the number of moles of solute per liter solution. That's sort of redundant. Okay, so here's our problem. We're going to calculate the molarity of a solution when 10 grams of sodium hydroxide are added to make enough water to make 100 milliliters of solution. Well, we know concentration is solute divided by solvent. So if we're given two values like this, solute and solvent, then we're going to put them one over the other to start our calculation. And then we just start making conversions to get to our moles per liter, because it is moles per liter. And so we get this calculation. So 10 grams of sodium hydroxide over 100 milliliters. Then we know that there's 1,000 milliliters per liter. Okay, so it's kind of different. If we start down to the right, then we can start putting the units up to the left. So we want the milliliters to cancel, so there's 1,000 milliliters per liter. Okay, and we know that there's 40 grams of sodium hydroxide in 1 mole of sodium hydroxide. And if we don't know where we get the 40 grams, it's our molar mass, and if we're still having difficulty in measuring our molar mass, we've got some studying we have to do. But that winds up with moles per liter. And that moles per liter is what this big M is. Big M means molarity. Okay, this means that means moles per liter, right there. And that is moles of sodium hydroxide. Moles of sodium hydroxide per liter of solution. That's how that works. Okay, so then we bring to how many grams. There's another way, other problems we can do. One of them is how many grams of sodium chloride would be needed to make 400 milliliters of a 0.6 molar NaCl solution. So we're going to start with the volume and then use the molarity as a conversion factor. So we'll start with 400 milliliters. Okay, we know that 400 milliliters. We'll start with 400 milliliters. We know that 1,000 milliliters equals a liter. And 1 liter equals 0.6 moles from this right here. This leads to this down here. Okay, but the liters are going to cancel. And the liters cancel. And the moles cancel with 1 mole of NaCl because we don't want moles anymore. We are looking for grams right here. So we know that 1 mole of NaCl is going to be 58.5 grams of NaCl. Again, that's our molar mass. And then we wind up with all of our units canceling except for our grams, which gives us 14.04 grams of NaCl. Now I apologize for my voice being scratchy. Again, it's late at night and my allergies are acting up and well, anyways. You don't need to hear all that. Okay, so the next version we have, by the way, molarity is going to be the predominant concentration you guys are going to use, and it's most chemical. It's the most used when we're doing chemical equations. Is based on molarity. The next one we're going to do is parts per million. This one is ridiculously easy if we've got grams per liter. Okay, once we have grams per liter, then we can convert to parts per million, and it's a piece of cake. Here's the idea. It's 1 part solute by mass per million parts of solvent by mass. Well, but since the density of water is 1 kilogram for every liter, and 1 kilogram of water equals 1,000 grams, which equals 1 million milligrams. Okay, that's the same liter of water. Then our parts per million in an aqueous solution is number of milligrams of solute per liter of water. That is our parts per million of solute to solvent. So our calculation is on the next page. We're going to calculate the parts per million in a solution containing 2.5 grams of salt and 650 milliliters of water. Well, we need to convert our grams to milligrams. That's going to be 2,500 milligrams multiplied by 1,000. And then convert milliliters to liters. And so we're going to divide by 1,000. So we therefore get 2,500 milligrams of NaCl over 0.650 liters, and that gives us 3,800 parts per million NaCl. And that's it. Okay, but of course we can always do another kind of equation where we give you the parts per million, and you have to figure out one of the other things. So we're going to calculate the number of grams of chlorine gas needed to mix with 500 milliliters of water to make a solution that is 400 ppm Cl2. Well, the 500, just like on the previous equation where we start with the conversion factor, we're going to take the 500 milliliters of water and then use the conversion factor to figure out the number of grams. And that looks like this. 500 mils of water, where we know that 500 mils of water, where we know that 100 mils of water equals 1 liter. And 1 liter is 400 milligrams of Cl2 from over here. Remember, this is milligrams per liter. And 1,000 milligrams equals 1 gram. And all of a sudden, there's our gram unit We're left with our gram unit, and that turns out to be 0.02 grams of Cl2. And that's pretty much it. Okay, trust your units. We should have some practice with this cross canceling by now. And you will have plenty of practice problems to accomplish. Okay. Finally, we have percent composition. This is just a mass ratio of the grams of solute or solvent to the total grams of solution. So the basic formula is this. It's the grams are solvent or solute. So that's not right. Oops. Okay, so I totally lied. That is right. We're looking for the percent composition. It can either be a percent composition of solute per solution or a percent composition of solvent per solution. So, and it's by mass. So if we have, let's say our solution is 99% water. Okay, that is because 99% of the mass is water and 1% of the mass is something else, which is the solute. So this is how you do it, right? Okay, or the other way of looking at it is part divided by whole times 100 equals a percentage. But that's just how you figure a percentage anyways. Okay, so sample problem. Calculate the percent composition of glucose in a solution made by dissolving 45 grams of glucose in 650 grams of water. Now, something to be careful of here. Remember, percentage is part divided by the whole. Well, the total mass of the solution is 45 plus 650, giving you 695 grams. Therefore, the percent of the glucose in the solution is 45 grams of glucose divided by 695 grams of solution. Okay, giving us 6.47% by mass. Okay, there you go. I've changed it for those of you that have difficulty with the percentage. So you take the fraction, 45 divided by 695 gives you this is a decimal. Then you're going to multiply that by 100, and that's how you're going to get your percentage. Okay. So here are the other ways of doing it. Calculate the mass needed to make 500 grams of solution. That's 8.5%. Where the part equals the percent times the whole divided by 100. So 8.5 times 500 divided by 100 times 500 grams divided by 100 equals 42.5. Or the other way of looking at it is 8.5% is really just 8.5 over 100. Okay, and then that's going to equal, and then we're going to multiply that by times times 500 grams. Okay, and that's going to equal our 42.5. grams. Okay, and here's another way of doing it where you can calculate the mass of sterling silver. Could be mixing 40 grams of, okay, blah, blah, blah. Sterling silver, 92.5 grams percentage, and then we figure out from there. Okay, but that is sitting there in front of you. I'll let you guys study it to see how that goes. Finally, we have dilution problems. This is the last kind of math that we're going to do for this, although this is the most confusing usually. We can change concentrations. In fact, in chemistry, we make our solutions by taking highly concentrated stuff and diluting it so it's safer to use in the lab. But it's more efficient to send chemicals at high concentrations. 12 molar, 18 molar, 18 molarity stuff. So it's 18 moles per liter or 12 moles per liter, particularly acids and bases and that sort of thing. And then when we start using it in class, we have to dilute it. And so we'll put more water into it and then measure stuff out and put more water into it. And the formula we use to figure out how much we're going to use is M1V1 equals M2V2. And I want to fix that. Okay, well, I don't know why that one is so ugly, but it's not letting me fix it. Alright, so we're going to use M1V1 equals M2V2, where M1 and M2 are molarities, not mass, and V1, V2 are volumes. Okay, so our sample calculation is this. We're going to calculate the volume of concentrated hydrochloric acid needed to make 500 milliliters of 3 molar hydrochloric acid. Well, using M1V1 equals M2V2, we're going to get this. Since M1V1 equals M2V2, 12 molar, we're going to take some volume of a 12 molar solution. To get that, we know that it needs to equal 0.5 liters of a 3 molar solution. So we multiply these moles times these liters, or this molarity times these liters, to give us 1.5 moles. And we're going to divide that by 12 molar to find V1. Okay, so simply solve for V1 is going to be your volume. It's going to be 3 times 0.5 divided by 12 is going to give us 0.15 liters or 125 milliliters. So what we would do is we would take 125 milliliters of our 12 molar solution and then dilute it to 500 milliliters, and that would give us a 3 molar solution of the same stuff. Okay, we can then continue this on, and that's where you'll see the next page of the notes. But I'm going to stop there because that's something we're going to do in class, and it's difficult to explain without actually drawing it on the board, and that's what I'm not doing here. So we'll pause. We'll stop here, and then we'll have one more piece of lecture after this.